Okay, so this is problem number 7, page 221. This is chapter 7. And we're just dealing with the kinematics information as far as angular quantities are concerned. So I'm just going to read the problem, and as I read it, I will draw a picture and it identifies some quantities. So I'm going to draw a circle just because in this chapter we're dealing with circular motion. So it says we have a machine part that rotates at an angular speed of 0.06 radians per second. So I'm going to show this arrow as omega. And so omega is equal to 0.06 radians per second. Okay, next point. Its speed is then increased to 2.2 radians per second. So we're going to call this omega 0. This is the initial rotational speed. And the rotational speed after rotating or after accelerating is going to be 2.2 radians per second. And it tells us that the angular acceleration, which is alpha, is going to be 0.70 radians per second squared. So we've got 3 out of the 5 quantities. The 2 things that we don't know are delta theta and time. So it says find the angle through which the part rotates before reaching its final speed. So there's delta theta is the angle. So they're asking, for part A, they're asking for what is delta theta, the angle. So we look at what we have, and we have the 4 equations, and let's just write them down. We have delta theta is equal to omega plus omega 0 over 2, which is the average value, times t. We have omega is equal to omega 0 plus alpha t. Let me just move those over so we can put them all in one space here. We have delta theta is omega 0 t plus 1/2 alpha t squared. And finally, omega squared is omega 0 squared plus 2 alpha delta theta. So those are the 4 equations. So the question is, which one do we need to use? Well, we aren't given any information about time, and they haven't asked us for it yet. They may ask us for it later, but the one that involves omega, omega 0, and alpha, and also delta theta, but not time, is this equation. So that's the one we're going to use. And so let's see what we're going to do. We're going to solve for delta theta. So we're going to take this equation and solve for delta theta. So what we have is you'll have omega squared, you'll subtract omega 0 squared. That will leave 2 alpha delta theta. So to solve for delta theta, we just divide by 2 alpha. And it's a positive angular acceleration because we're increasing the angular speed. So let me put another page up here so we can see this. Oh, sorry. So now we just need to plug the numbers in. So delta theta, the angle through which it rotates, is omega, 2.2 radians per second. We square that. We subtract off omega 0, 0.06 radians per second. We square that. And we divide by 2 times alpha, which is 0.70 radians per second squared. So we plug those numbers in. We get 2.2, oops, got to turn my calculator on. 2.2 squared minus 0.06 squared divided by 2 divided by 0.7. And so we get delta theta of 3.45 radians. The second squared here cancels out with the second squared there, so we just end up with radians. And that's about half a revolution, because a full revolution is 2 pi, which is about 6 point something, and so pi, which is half a revolution, is 3.14, and so it's just slightly more than half a revolution. Okay, it says in general, if both the initial and final angular speed are doubled at the same angular acceleration by what factor is the angular displacement changed? And actually, I think we worked this in class, but it's not such a bad thing to work it again. So what we're saying is, let's say we have another omega that we double. So we're going to say, instead of having omega, we're going to have 2 omega. And if instead of omega 0, we're going to have 2 omega 0. So we're doubling the rotational speed. But at the same, alpha is going to be alpha. So we're going to keep alpha the same, but we're going to increase the angular velocities by 2. So we can plug that into our original equation, and we have delta theta is omega. So instead of omega, we've got 2 omega, and instead of omega 0, we have 2 omega 0. We still divide by 2 alpha. We don't divide by 2 times 2 alpha. And so, since we can multiply this out, we get this, and you can see this is the same as 4 times omega squared minus omega 0 squared, all divided by 2 alpha. And therefore, we'll call this delta theta prime. You can see that, so this is delta theta prime. This is where the angular speeds have doubled. So delta theta prime is equal to 4 times delta theta. So by increasing the angular speed, initially and finally, we are quadrupling the change in the angular, the change in delta theta. This is problem 6 from page 221, chapter 7. So what we have is a centrifuge in a medical laboratory rotating at an angular speed of 3,600 RPM. And then it's turned off and it rotates until it comes to rest. So the conditions we know based on the problem are that omega 0, the initial speed is 3,600 RPM, which is revolutions per minute. And the final angular speed is going to be 0. And that doesn't matter radians per second, because we're going to convert omega 0 to radians per second. And you do that by having 60 seconds per minute and 2 pi radians per revolution. So let's just convert that. So 3,600 revs per minute. And usually you can remember because revolutions per minute is going to be higher than radians per second. But anyway, so you know you multiply by 2 pi and divide by 60. But we're going to go ahead and figure it out here if you forget that. So you look at the units, and we're going to have minutes per second. That's the way so that the minutes cancel out, and we end up with seconds. So we usually don't remember how many minutes per second, but we remember how many seconds per minute. So we put 60 next to seconds and 1 there. So that'll mean now revolutions per second. And then what we have to do is we have to have revolutions in the denominator and radians in the numerator. So there are 2 pi radians per revolution. And let me find my calculator. And if we do that, we get 3,600 divided by 60 times 2 times pi. And it's usually close to a factor of 10. I just realized, oh no, that's correct. So it's 377 radians per second. One thing I have to remember is radians are unitless. A radian is the ratio of the distance traveled around the circumference of the arc divided by the radius. And so they're both in inches or feet or whatever. So radians are actually unitless. Sometimes omega is just shown as 1/seconds. But I'm going to explicitly show radians here. Okay, so we have omega 0, we have omega, and let's see what else we have. Well, it says we go through 50 revolutions, so that is the angular displacement. Delta theta is equal to 50 revolutions. And again, we can convert that to radians, 2 pi radians per revolution. And so we get 2 times pi times 50. So 50 revolutions is going to be 314 radians. So we know 3 out of the 5. The other things we don't know are the acceleration and the time. So let's go ahead and calculate both of them. We don't have to calculate time according to the problem, but we'll go ahead and do it anyway. We'll do the acceleration first. So thinking about the equations, the one that first comes to mind is this one, which says omega is equal to the initial angular speed plus alpha, the angular acceleration times time. But that has both time and alpha in it, so that's not going to work. Let's think about it. Oh, that's the one that we use, this one, which we use the equivalent form of it in linear stuff. So that was 2 alpha delta theta. So we have the 2 omegas and we have delta theta, so we can solve for alpha algebraically. So what you get is you get omega squared minus omega 0 squared divided by 2 delta theta. Now this thing's slowing down, so we should get a negative alpha. When things speed up, positive alpha. Slowing down, negative alpha. So this should be negative, so hopefully that's what's going to happen. So we just plug the numbers in. Omega is 0 radians per second. Quantity squared, subtract omega 0, which, let's go back to the beginning, and it was 377. So 377 radians per second, quantity squared divided by 2 times delta theta, and the change in theta was 314 radians. And so the units are going to be radians squared per second squared divided by radians, with radians per second squared, which is the correct units. And we do have a negative sign. So let's plug that in here. So put the negative in at the end. 377 squared divided by 2 divided by 314. And so alpha is equal to negative 226 radians per second squared. And let's see if that makes sense. We haven't made any mistakes. And you know, it's moving pretty good at the beginning. 3,600 RPM is moving pretty good. 50 revolutions. It's a little hard to figure out exactly. You know, we have kind of we have the acceleration due to gravity in linear to kind of give us a ballpark, and sometimes we don't have the same feeling. Okay, now we can use that other equation to solve for time. So that was omega equals omega 0 plus alpha t. So if you solve for time, you'll have omega minus omega 0 over alpha. So the time it takes to slow down, omega was 0. Omega 0 was 377 radians per second. And we divide by negative 226 radians per second squared. And so the time it takes to slow down is pretty quickly, so that actually kind of goes along with what we were thinking. That was a fairly large acceleration, negative acceleration, so I get 1.7 seconds. So obviously they put some kind of braking mechanism on this. It wouldn't slow down that quickly. So that's the solution to the problem. Okay, we're going to do problem number 12, chapter 7, page 221 for physics. So problem number 12 says that we have a disk, 45 centimeter disk. So let's write that down. Diameter 45 centimeters. Let's go ahead and convert that to meters. So that would be 0.45 meters. That's the diameter. We may convert that to radius in just a second. Rotates with a constant angular acceleration, so alpha is equal to 2.50 radians per second squared. It starts from rest at t equals 0, and a line drawn from the center of the disk to point P on the rim of the disk makes an angle of 57.3 degrees with the positive x-axis at this time. Okay, so what it's saying is theta 0 is equal to 1 radian. 57.3 degrees is 1 radian. You can do that by converting degrees to radians. Okay. And then we're going to have some theta at some later time, which I guess we're going to figure out. Okay, so it says at t equals 2.3 seconds, find the angular speed of the wheel, the linear velocity and tangential acceleration of p, and the position p in degrees with respect to the positive x-axis. Okay. So we're going to need to, let's see what we have. We have alpha. We have, let's see, did they give the initial angular? It starts from rest, so we know that omega 0 equals 0 radians per second, and alpha is positive, so it's speeding up. What else do we need to know? Oh, we have time. Time is equal to 2.3 seconds. Okay, so what we need to do first is find omega, which is the angular speed at 2.3 seconds. So let me just underline what we know here. As far as we know alpha, we know omega 0, and we know time. So we should be able to calculate omega at this. And so looking at these three properties, I think we're going to use this one, which is the second equation. Omega equals omega 0 plus alpha t. And so we can solve directly. We don't have to actually do any algebra because what we need is on the left-hand side. So omega 0 is 0. Excuse me. Alpha is 2.5 radians per second squared. And the time is 2.3 seconds. So our angular speed, let's multiply this together, is 2.5 times 2.3. 5.75. 5.75, and the units are radians per second. So that's the answer for part A. Okay, the second part of the question asks for the linear velocity and tangential acceleration of p. Okay, so the relationships between angular and linear speeds are as such. So what we have is we have that v, the linear speed, is equal to the angular speed times the radius. And we were given the diameter, so we're going to have to, the radius is going to be 1/2 the diameter. And if we go back to the beginning, it was 0.45 meters, so the radius is 0.225 meters. That's half of 0.45. So our linear speed, we just take what we just calculated, 5.75 radians per second, and we multiply by the radius of 0.225 meters. And radians, again, is dimensionless, so when we multiply these together, we get meters per second. So 5.75 times 0.225 is 1.29 meters per second. Now the acceleration, the tangential acceleration, we'll call it alpha sub t, is just equal to, oh, sorry, wrong thing here. The tangential acceleration is just equal to alpha times r. So we've already calculated, we already had alpha specified as 2.5. So the linear tangential acceleration is just 2.5, and it was radians per second squared times the radius, which is 0.225 meters. And so we multiply those together, 2.5 times 0.225, we get 0.56 meters per second squared. Again, the radians disappear because they're unitless. Okay, so that is the linear velocity and tangential acceleration. The actual centripetal acceleration we say don't ask for, but if we wanted to find the centripetal acceleration, it would just be v tangential squared over r. So we can plug that in and find it out. Okay, the last question says position p in degrees of the respective positive axis. So what we do is we find out what delta theta is. Delta theta is going to be equal to omega plus omega 0 divided by 2 times time. So delta theta is equal to omega, which was, let's go back up here, somewhere 5.75 radians per second plus omega 0, which is 0 radians per second, divided by 2 times time, which was, what was the time? 2.3 seconds. 2.3 seconds. And the units will work out to be radians. So we have 5.75. Okay, so I'm going to do problem number 7 on page 221. I'm not going to rewrite the problem. I'm just going to write down the important facts. So if you can turn to your page, turn to the book to that page. Okay. So it says we have a machine part that rotates with an angular speed of 0.06 radians per second. Actually, that looks like a problem I've done before, so we're not going to do that one. So I'm going to work through a problem that's not in the notes and one that's also not in the homework. Just to demonstrate how you use the kinematic equations for rotation and motion. So this is problem number 10, and it's on page 221. And I'm going to read the problem, and I'm going to ask you to read along, and we'll pick out the pertinent information. So it says that the tub of washer goes into the spin-dry cycle, starting from rest and reaching an angular speed of 5 revolutions per second in 8 seconds. So we're going to have the first part, and we'll call that part A. So it starts from rest, so that means the initial speed, angular speed, is 0 radians per second. It says it speeds up to 5 revolutions per second, and that it takes 8 seconds. So we've got 3 quantities, 3 of the 5 that we normally deal with. The other ones are acceleration, the angular acceleration, and the delta theta. Now, before we move on, we have to make these in consistent units, and so we want to change revolutions per second into radians per second. And so the only difference, let's see, is it revolutions per second? Yep. Okay, so we don't have to change seconds, we just have to change to radians, and there are 2 pi radians per revolution. So all we have to do is take 2 pi times 5, and that will give us the number of radians per second. So we have 2 times pi times 5, and so that's 31.4. 31.4 radians per second. Okay, so everything's in the good units here. So that's the first thing that we do. And so we can calculate the angular acceleration and delta theta. We'll come back to that in a second. Well, actually, let's go ahead and solve it. So we need to calculate, what they're asking for is through how many revolutions does the tub turn during the entire 20-second interval. assume constant acceleration while it is turned, starting and stopping. So we have to think about which equation applies here. And actually, it's the first equation that we have, which says that the change in the angle theta is equal to omega plus omega 0 divided by 2, which is the average for that time period, times the time. So delta theta is equal to 0, actually omega is 5. It doesn't really matter which order we do it in, but we'd have 31.4 radians per second minus 0 radians per second divided by 2 times the time, which is 8 seconds. So delta theta, you can follow along and plug them into your calculator, make sure you can do this correctly. But I get 125 radians. Then we're going to have to convert that to revolutions later, but we'll do that when we finish finding the whole thing. Okay, so the second part of the process is we start off with 5 revolutions per second, and we'll just leave it in radians per second. So omega 0 for the second part is 31.4 radians per second. The final speed is 0 because it stops. And the time it takes is 12 seconds, so we have t equals 12. And so we can use the same equation. Delta theta is equal to, so even though we go from the same initial to the same final angular, the same difference basically. So omega 0 is 31.4. Actually, omega is actually 0, so that is correct. 0 radians per second plus 31.4 radians per second divided by 2 times the time, which in this case is 12 seconds. And so the change in angle theta when it slows down, 31.4 times 12 divided by 2 is 188 radians. And so it's still going in the same direction, so the total is going to be A and B. So let me go call this A, and we'll call this B, theta, delta theta and delta theta B. So the total change is A plus B. And so we have 125 plus 188. Those are both radians, so let's put those in there. 125 plus 188. 313 radians, and we just have to divide by 2 pi. So in terms of revolutions, we take 313 divided by 2 divided by pi, and we get 49.8. So we'll round it off to 50 revolutions. So that's pretty much it for the problem. I can't think there's nothing else. They don't ask you for the accelerations. We could calculate the acceleration. How would we do that? Well, let's think. V is equal to V0 plus, using the wrong units here. Gotta make sure I use omega. So omega is equal to omega 0 plus alpha t. So you could solve for alpha. Alpha would be omega minus omega 0 over t. And we have all that information. So we could calculate the angular accelerations. It accelerates more quickly than it slows down because the time is less. Okay, we're going to do problem number 14, which is one of the homework problems. So we have an electric motor rotating the workshop grinding wheel at a rate of 1.0 times 10 to the second revolutions per minute. So it starts off, it's originally off, so it's the original rotational speed is going to be 0 radians per second. And, oh, actually, it's already running, so let's not do that. So the original rotational speed is 100 revolutions per minute, RPM. And so let's go ahead and convert that to radians per second. So let's see what we have. We have 100 revolutions per minute. And we're going to multiply by either 2 pi or 60 and divide by the other one. So the question is, which one do we do? And so we can sort of figure that out here just by doing this time one first. So we have 60 seconds per 1 minute. So that means 2 pi has to go on the other side in the numerator. So it's 2 pi radians per revolution. So radians per second are less than revolutions per minute. That's one thing we can kind of remember. So we have 100 divided by 60 times 2 times pi. So we have 10.5 radians per second. So that's the initial, and then we turn it off and it's going to slow down, just like the wheel that we're doing in the lab today. We had an initial angular speed and then it went to 0. So we know that omega, which is the final speed, is going to be stationary, which is 0 radians per second. And it says we have a negative acceleration, that's because it's slowing down, of negative 2.00 radians per second squared. So we have 3 things. We have initial angular speed, final angular speed, and the angular acceleration. So the other variables we can find through those 4 equations. And rather than just assuming that we know which one to use, let's just write them down. So we have delta theta is equal to omega plus omega 0 divided by 2 times the whole thing times time. We have omega is equal to omega 0 plus alpha t. Delta theta is omega 0 t plus 1/2 alpha t squared. Let me fix the 2 there. And finally we have that omega squared is omega 0 squared plus 2 alpha delta theta. So these are the 3 things that we know, and what are they asking for in this problem? They're asking for how long does it take for the grinding mill to stop, so that's time. So let's see. This one's not going to work because we know this and we know that, but we don't know 2 other things. This one, we know alpha, omega, omega 0, and time, so that's the one we're going to use. Let's just look at the other ones to see why we can't use them. Here we know omega 0, we know alpha, but we don't know time or delta theta, so that doesn't work. And here we know omega, omega 0, we know alpha, so we can calculate delta theta, but they're not asking for delta theta, at least not right now. For the next part they are, so we could use this one. But actually, once we find 4 out of the 5, we can use any of the equations to find the other remaining unknowns. So we're going to use this one, and if we solve for time, we'll have omega minus omega 0 divided by alpha. So omega 0 is 10.5 radians per second. Alpha is negative 2.00 radians per second squared. And that works out good because we always have positive time, so you know you've made a mistake with signs if you have a negative time. So negative 10.5 divided by negative 2 is 5.25 seconds. So that's the time. Now, we could use this one with the original information to solve for delta theta, but that's a little more complicated than it needs to be. So I think we could use this expression, the first expression, because that doesn't involve squaring anything, so it's a little easier. So to find delta theta, and they're asking for how many radians. So all we have to do is use omega plus omega 0 divided by 2, and the whole thing times the time. So we plug those in. Omega 0 10.5. So actually you have to add that. So 10.5 radians per second divided by 2. And then you move that over a little bit. And then we multiply that by the time, which is 5.25 seconds. And the units work out because seconds cancel out, and we just end up with radians. So if we plug it into our calculator, 10.5 times 5.25 divided by 2, we get 27.6 radians. And how many revolutions? They won't ask for this, but how many revolutions? All you have to do is divide by 2 pi. So we have 27.6 radians divided by 2 pi radians per revolution. And put that in our calculator, and we get 4.4 revolutions. 4.4 revs. This is the actual question. What's this? Delta theta. And that's it. Okay, this is problem 18, chapter 7. So this is a centrifugal acceleration problem. And I've already worked it once and made a mistake because I forgot to convert units, so I have to be careful. Anyway, if you read it, we need a acceleration equal to 20g. So we take 20 times 9.8 meters per second squared. So 20 times 9.8, that's 196 meters per second squared. And the centripetal acceleration is because of something rotating, has a tangential velocity, and there are two ways of coming up with that. You can write it as the tangential velocity squared over r, or omega squared r, where this is the angular velocity. Well, in our case, they're asking for rotational speed, which is angular velocity. It's in the units of revolutions per minute instead of normal, which is radians per second. We also have to convert the radius, and that was my problem. I forgot to convert feet to meters. So if you go to the front of the book looking for the conversion, there are 3.281 feet per meter. So we're going to divide, let's multiply by 3.281 feet per meter. I do the opposite way because I need to cancel out the feet. So 29 feet divided by 3.281, I get 8.84 meters. Okay, so we're going to use this form. And so if you solve for omega, you see I divide both sides by r and take the square root. So I have the centripetal acceleration divided by r. So omega is the square root of 196 meters per second squared divided by r, which is 8.84 meters. So you can see the meters cancel out. We get 1 over second squared for the units, and then you take the square root, so you get 1 over seconds. 196 divided by 8.84, take the square root, and I get 4.7 radians per second. And the problem asks for revolutions per minute, so I need to convert this radians per second. And the conversion seconds, I need that in the numerator, minute in the denominator, and then radians I need in the denominator, and revolutions in the numerator. So I have 60 seconds per minute, 1 minute, and I have 2 pi radians per 1 revolution. So when you multiply that out, 4.7 times 60 divided by 2 divided by pi, and I get 45 revolutions per minute, or you could say 45 revolutions per minute. You have to be careful. If we used M, we wouldn't know if that was meters or minutes, so you have to kind of write it out. Okay, this is Chapter 7, problem number 23. So we have a certain light truck going around a flat curve having a radius of 150 meters. So I'm just going to draw a circle, and here is the center of the circle, and here is the radius of the circle. And because it's going around a circle, we can use centripetal acceleration only. So there's the car, the tires, and the radius is 150 meters. And the maximum speed, so that would be the tangential velocity of 32 meters per second. With what rate, maximum speed can it go around a curve having a radius of 75 meters? So what's going to happen is if you have a smaller radius, you're going to have a smaller velocity. And the thing that's limiting it is basically comes down to you've got a certain force, tangential force, or centripetal force, if you want to call it that really, because it's centripetal force, and that's equal to the mass of the truck times the centripetal acceleration. And so there's a maximum force, which also, because the mass of the truck stays the same, there's going to be some maximum value for that, whatever that is. So in this particular case, we can have, the tangential velocity squared for case 1 divided by the radius for case 1, which is going to be the centripetal acceleration, and then you have the second case for the squared over the radius. That means that the force is what's limiting it. The force is limited by the acceleration, and the acceleration is v squared over r. And so we can just say this is going to be this maximum value is going to be a constant value. It's basically how much friction can the tires produce in the direction, perpendicular to the direction it's going. So all we have to do in this case is, if we want to solve for, I guess V2 is the maximum, so we could say V2 tangential squared is equal to V tangential 1 squared, and then we have R2 over R1. Did I get that right? Yeah, okay. So, and then we can take the square root, so square root of this thing so in our case, V tangential 1 is 32, R1 is 150, and then we have V tangential 2 is question mark, R2 is 75 meters. So we can plug those in. So our limiting speed is the square root of 32.0 meters per second squared. R2 is 75 meters, and R1 is 150 meters. They put 75.0 so that we can keep 3 significant figures. So it should be smaller, because you can, the tighter the radius, the smaller you have, the slower you have to go. So 32 squared times 75 divided by 150, take the square root, and I end up with 22.6 meters per second. And let's just check the answer here. That's correct. Okay, chapter 725. So we have a 50 kilograms child standing in the rim of a merry-go-round. So let's make a circle again. So here's the child. And we'll say the mass is 50.0 kilograms. We have a radius for the problem. And that radius is 2 meters, 2.00 meters. That's R. Rotating with an angular speed of 3 radians per second. So omega is 3.00 radians per second. What's the child's centripetal acceleration? Okay, we have two forms. We have V tangential squared over R, and we have omega squared R. So this one makes most sense to use because that's what we have, omega. And the units are correct in radians per second, not revolutions per minute, so that works out great. And the centripetal acceleration is not dependent upon the mass. The centripetal force is dependent upon the mass. So omega is 3.00 radians per second. And we square that, we multiply by R, which is 2.00 meters. So for that child to stay in, let's say orbit, it's not really orbit, so we get 18, and the units are meters per second squared. Meters, and then we get second squared. Radians does not have units. Okay, which is almost 2g, 2 times the acceleration. It's a little less than 2 g's. Okay, now what are they asking for? What is the minimum force between her feet and the floor of the carousel that is required to keep her in the circular path? So what happens is you've got to have a force pushing in this direction, the centripetal force, that causes the centripetal acceleration. So that's the force between her feet and the merry-go-round. So the centripetal force is just equal to the centripetal acceleration times the mass. Force equals mass times acceleration. I guess I should have put those in different order. And we know our mass 50 kilograms, so let's correct the order there. Mass times centripetal acceleration, 50 kilograms times 18 meters per second squared. 50 times 18, 900 newtons. Okay, what minimum coefficient of static friction is required? Is the answer you found reasonable? In other words, is she likely to stay in the merry-go-round? Well, if you think about this person, here they are, and so you have this centripetal acceleration that's going towards the center, and so you've also got this force which is due to friction. So this is the friction force which is pushing in the same direction, and the friction force has to equal 900 newtons. So what you're going to have is you're going to have a normal force that's pushing down. So this is, well, you're going to have the weight, and then you're going to have a normal force pushing up like this. So this is the weight, which is the mass times g, and the normal force is equal to the weight, just from the sum of the forces in the y direction. So the weight is going to be equal to the mass, which is 50 kilograms, times g, which is 9.8 meters per second squared. So 50 times 9.8 is 490. 490 newtons. So if we take the ratio of these, this would give us the coefficient of friction we have to have for this to be true, the minimum coefficient of friction. So it would be the friction force divided by the normal force. The friction force is what we need to keep it in circular motion. So you'd have 900 newtons divided by the normal force that's available to us. So 900 divided by 490 is 1.8. So the question is that a reasonable coefficient of friction? And the answer is not really. Note, if you remember, we had coefficient of frictions of 0.3 or 0.4, and even with rubber, I think it was 0.9. So this is too large, and therefore her weight is not big enough to create enough friction force. So let's say her friction, let's just assume that, assume mu is 1, which is pretty large anyway. We would say the corresponding friction force would be 1 mu times the normal force, which is 490, and you'd get 490. So that's all the force you can get from friction, and we need 900. So how do you get that additional force? Well, you could hold on. She could be holding on to something. You could push down on her. Put some mass. Well, that wouldn't help any. You'd still have. So you could have somebody externally push down on her. So somebody next to her could push down on her shoulders, I think. And the problem with that is the person pushing down, when they push down, their weight, their normal force would become less, and they'd be more likely to fly off. So most likely she'd have to hold on to something. Okay, let's just check the answer here. This is problem 25. So let's see what they say. Okay, so they get centripetal acceleration of 18, which is what we got. You get a centripetal force of 900. You get a coefficient of friction of 1.84. So large a coefficient of friction is unreasonable, and she will not be able to stay on the merry-go-round, which is exactly what we just said. Interesting. Okay, next problem. 7-31. So what we have is a child on a Ferris wheel. So this is in the vertical plane. So it's a 40-kilogram child, takes a Ferris wheel that rotates 4 times each minute. So omega is 4 revolutions per minute. And let's say the mass of the child is 40.0 kilograms. And the diameter is 18 feet. So we're always worried about the radius. So the radius of the Ferris wheel is half of 18, which is 9 meters. That's R. What is the centripetal acceleration of the child? Well, again, we have 2 forms of centripetal acceleration. There's that, and there's that. So because we're given omega, it's probably easiest to do that form, but we do need to convert omega. 4 revolutions per minute, and again, we need minutes per second to cancel those out to get seconds, and then we need revolutions per radian, radians per revolution. Those cancel out. So minutes per second, 60 seconds per 1 minute, 2 pi radians per 1 revolution. So what do we get here? 4 times 2 times pi divided by 60 is 0.418 radians per second. Okay, so that's omega. So the centripetal acceleration is just omega squared times R, and that'll give us meters per second squared. So we get 1.58 meters per second squared. Okay, so that's the centripetal acceleration. You see it's, maybe 1/5 of a g, something like that. And that'll constantly be pointing inwards no matter where you are. So the centripetal acceleration is always pointing towards the center. And likewise, there'll be a centripetal force that's pushing towards the center as well. Okay. What force, magnitude, and direction does the seat exert on the child at the lowest point in the ride? So that's right here. So let's draw a picture of the child. Let's draw a free body diagram of the child. So what you're going to have is you're going to have a force. This is the normal force, which is the force of the seat on the child. You're going to have the weight, which is going in this direction. That's a non-contact force, and that's equal to the child's mass times the acceleration due to gravity. And then you're going to have a centripetal acceleration. And at the lowest point, let's just define this as positive y. There's no x forces because the weight's in the positive direction and the centripetal acceleration is in the vertical direction. So we get 1.58 meters per second squared. So that's acceleration. Now the centripetal force, we don't put that on there because that comes through here. So you have to be a little careful about that. So if you do the sum of the forces in the y direction, they don't equal 0. Even though the velocity in the y direction is 0, you have you still have an acceleration because you're changing from going down to going up. Your magnitude of your velocity, your tangential velocity is constant, but you have a change in the direction. Okay, so you have the mass times acceleration in the y direction, which in this case is a centripetal acceleration. And that's equal to the sum of the forces, and we have the normal force pushing up, and we have the weight pushing down. The normal force is what we're trying to solve for. So the normal force is the mass times a sub y plus w. So we just plug in what we know. The mass is 40 kilograms. Acceleration in the y direction. Well, a sub y is in this direction because it's towards the center of rotation, and therefore it's positive, and it's a positive 1.58 meters per second squared. Weight is always positive, so it's the mass times the acceleration due to gravity, which is positive. And so what happens is when they're at the bottom of the thing, the seat pushes up to match the weight, but it also has to provide the centripetal acceleration. So you feel heavier at the bottom and lighter at the top. It's kind of like when you take a roller coaster. If you take a roller coaster and you have a hump that's pointing up, then you feel less weight. If you have a hump that's pointing down, or a dip, then you feel more weight. You feel like you're heavier. So we find out, the question was, what is the force? And the force is 455 newtons. That's compared to the weight which is 40 times 9.8. So 392 newtons is the weight, and then you get that extra bit from the centripetal force, centripetal acceleration. This is what force does the seat exert on the child when the child is halfway between the top and the bottom. Well, if you're in this, let me draw the picture again. If you're here and you draw your radius from there, at this point you have a centripetal acceleration in this direction, and then you have your weight, which is pushing down here. So the centripetal acceleration halfway up doesn't contribute anything to the weight. At the top, it subtracts from the weight, so you feel less weight. When you come at the bottom, you feel more weight. In the middle, the centripetal acceleration pushes you towards, the seat is pushing you towards the center to keep you in a circle. So part 3 is just equal to the weight, which is 392 newtons. If you were at the top, then you would have 392 minus the difference between these two, which was 55 plus 7, 8, 63. So you'd have 392 minus 68, or whatever it is, 63. Okay, so that's the answer for part C. Or part D. Oh, I forgot the highest part. Okay, so I missed the part. This is part D. For part C, what you do is you would have the normal force would be equal to the weight minus the mass times the centripetal acceleration. So you'd have 392 minus 40 times 1.58. 392 minus 40 times 1.58, which is 329. 329, so you feel less weight at the top. So let me just double check here. This is problem number 32. So let's zoom in through here. Oh, 31. I forget what I was doing. So the answers are given. There's 455, yes. 329, yes. And oh, actually they want the angle. I didn't see that. Okay. So the one that says, what force does this, oh, okay. Sorry. There actually are, the force upward is 329, or 392. So you've really got two forces in the case of the third part. So you got a sideward force and a upward force. So what you're going to have is you're going to have a normal force which is pushing up, and then you're going to have a force which is going to be, let's see, which way is the force pushing? It's going to be pushing towards the center. Make sure I get that right. Let's think about that. So here we are, and so you've got the weight, which is then going to have a corresponding normal force, and then you have a friction force, which is pushing inward, like that. Yeah, because if you didn't have that friction force, you'd go straight out. So the corresponding force is the vector sum of these two. This one is 392, which is just the weight, and this one is the difference between the two. 392 minus 329, 63. So that's 63 newtons. So the total force, this F here, is the sum of the squares. So you get 392 newtons squared plus 63 newtons squared. 392 squared plus 63 squared, square root 397. And you know, the question is it this angle or is it that angle? I think they look at this angle. And so you do the tangent. So you'd say the tangent of theta is the opposite over the adjacent. So theta would be the inverse tangent of 392 over 63. Make sure you're in degrees, which I'm not. So inverse tangent of 392 divided by 63 is 80.9. So that would be this angle right here. Let me just double check, make sure that's right. 80.9, 397. Okay. Okay, well I'm going to do, in this session, I'm doing problem number 32 on page 233. And this involves a roller coaster. Problem 32, page 223. And so I'll let you look at your book. It says a roller coaster vehicle has a mass of 500 kilograms when fully loaded with passengers. A, if the vehicle has a speed of 20 meters per second at point A, what is the force of the track on the vehicle at this point? Point B is what is the maximum speed the vehicle can have at point B for gravity to hold it on the track? So both of these involve centripetal acceleration. Part A, at the bottom of the track, we have two forces acting on the body. We have the weight and we have the centripetal acceleration. So I'm going to show the weight associated with that. And so the weight is just the mass times acceleration due to gravity. And the centripetal force is the force that's required to hold this thing in a circular path. So there's going to be another force, which I'm going to show as this vector. And so that force, the centripetal force, is equal to mass times the centripetal acceleration. And at the bottom, it's the sum of the weight and the centripetal acceleration. So let's go ahead and calculate the weight. The weight is just, again, mass times acceleration due to gravity at that particular point. We have 500 kilograms for the body. And we have an acceleration due to gravity, which we use all the time, 9.8 meters per second squared. So getting out the calculator, 500 times 9.8, it's 4,900 newtons. Okay, so that's one component of the force. The second component is associated with the centripetal acceleration. And because we're given velocities instead of angular speeds, we can use this form for the centripetal acceleration. It's just going to be equal to v squared over r, which is the linear speed. And our velocity in this particular case is 20 meters per second. And we square that and we divide by the radius, which according to the graph has a radius of 10 meters. So our centripetal acceleration is 20 squared divided by 10. So that's 40. And the units are meters per second squared. We have meters squared per second squared divided by meters gives us meters per second squared. And so that acceleration associated with the mass, or centripetal force, is just our mass times our centripetal acceleration. The mass is the same as we had before, so we have 500 kilograms times the centripetal acceleration, which is 40 meters per second squared, and therefore we have 500 times 40, it's 20,000, so it's considerably more. And so the total, what does it say, what is the force? So the total force is going to be equal to the centripetal force plus the weight. So we just add those two quantities, 4,900 newtons plus 20,000 newtons. And so we can add this together, it's 24,900 newtons. Now, the next part, as we go up the hill, the speed is going to go down. And it's probably a good thing, because if we maintain that speed, we probably would actually be the case where we would have it come up the track if that were the case. So let's just add a new page. And let's show both pages. So at the top of the arc, what we have is we have the same two forces, except the centripetal force will now be going in the opposite direction. So if I draw the weight's still pushing down, and then we have the centripetal force, which is pushing up because of the way the curvature is. So again, the weight is mass times gravity. The centripetal force is mass times velocity squared over r. And at this point, when they're equal to each other, the vehicle, according to this problem, the vehicle is just staying on the track. So we're going to set these two equal to each other. So we'd have mass times velocity squared over r is going to be equal to the mass times the acceleration due to gravity. You see the masses cancel out, and we can solve for the velocity, but let's first, so it's going to be equal to the radius times g, and so if we take the square root, we would get the square root of r times g. So now we can plug things in. We get the square root of r, which is 15 meters, write down 10. 15 meters times the acceleration due to gravity, which is what's causing it to be held down on the track, meters per second squared. And you can see we're going to get the units to work out because we'll have meters times meters, so we'll have meters squared per second squared, and take the square root of that to get meters per second. So plug that in our calculator. So we have the square root of 15 times 9.8, and we get 12.1 meters per second. Sorry for the color change there. I accidentally pushed the wrong color. So that is the maximum velocity that we can have at the top of that curvature. And you could kind of guess, you could use conservation of energy to figure out what the elevation change would have to be as a minimum to reduce the velocity from 20 meters per second squared to 12 meters per second squared. But we're not going to do that in this problem. This is problem 36. So we have a star which says collapses to white dwarf state. It says that in this state it would have approximately the same mass as it has now, but its radius would be equal to the radius of the Earth. So we need to know what the radius of the Earth is, and that is in the back of the book. So if you go to the back page and you look under radius of Earth, that's 6.38 times 10 to the 6th meters. Okay, and we need to know the mass of the Sun. So the mass of the Sun, where is the mass of the Sun? Well, let's see. Do we need to know the mass of the Sun, or can we look at the let's think here. The mass of the Sun. Because if you think about it, the density is the mass per unit volume. And we can calculate the volume from the radius. We need to know the mass of the Sun. So I'm thinking we could calculate it, or we could calculate it from the information about the rotational characteristics of the Earth. I'm not sure if that's what they're looking for us to do, so let me put a pause here and see what how they want us to find it. Whether they want us to just look it up somewhere. It might be given in a previous problem, or we could calculate it from the rotational properties of the Earth. So let me pause for a second. Okay, well, it turns out that the mass of the Sun is in the book. It's on page 217. So I'm looking through their Sun mass, 1.991 times 10 to the 30th, and the units are kilograms. Okay, so the density is mass per unit volume. Volume for a sphere is 4/3 pi r cubed. So let's go ahead and calculate the volume of the Sun. 4/3 pi times, in this case we're using the radius of the Earth, not the radius of the current Sun, because it's going to be much more dense. And we cube that. Okay. Getting the calculator out of my bag again. Okay, 4 divided by 3 times pi. Oops, what did I do there? Oh, I pushed the wrong button. Four-thirds times pi times the quantity 6.38 e to the 6th, all the raised to the 3rd power. Okay, so the volume is 1.09 times 10 to the 21st meters cubed. So the density would be the mass, which is 1.991 times 10 to the 30th kilograms, divided by 1.09 times 10 to the 21st meters cubed. 1.991 e to the 30th divided by 1.09 e to the 21st power. And I'm going to put this in scientific notation. So if you look on your calculator, you get 1.8266055505. So we count from the 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9th kilograms per meter cubed. How big is that? Well, the density of water is 1,000. So that's 10 to the 3rd. So it's 1,000,000 times more dense than water is. Okay, let's check the answer before we go on. 1.83 times 10 to the 9th. Okay, they're off just one decimal, one digit. I'm not sure what the difference is. Okay, back to the problem. So, problem 36. What is the surface free fall acceleration? Well, we have that g is equal to the universal gravitational constant times the mass of the object, which in this case is the mass of the Sun, divided by the radius. Divided by the radius squared. Radius squared. Pretty sure. Yes. Weight is m times g. The only thing we're missing here is m, so that works out right. So the acceleration due to gravity is g, which we get from the back of the book. If we don't remember what it is, 6.67 times 10 to the minus 11th power. The units are Newton meter squared per kilogram times the mass of the Sun, which is 1.991 times 10 to the 30th. That's in the back of the, actually it's in the chapter. I wrote it down over here on the left. Divided by the radius squared. So the radius is the radius of the Earth. We're saying it collapses to the size of the Earth. So 6 meters quantity squared. Okay, let's plug that in. Calculator. 6.67 e to the negative 11 times 1.991 e to the 30th divided by the quantity 6.38 e to the 6th squared. And I get the G is 3.3 times 10 to the 1, 2, 3, 4, 5, 6 meters per second squared, which compares with 9.8 meters per second squared. So it's huge, huge G. Let's check it out. 3.26 times 10 to the 6. Okay, that's close. About what I got. And the final, the gravitational potential energy associated with a 1 kilogram object at the surface. So the gravitational potential energy is equal to negative G times, let's see, I got the equation. So I'm going to go to the summary because it's always a good place to look for equations. Potential energy minus G, mass of the sun in this case, times the mass of the object divided by R. So we have negative G, 6.67. This is the universal gravitational constant. Meters squared per kilogram times the mass of the sun, which we have right here, 1.991 times 10 to the 30th kilograms times the mass of the object, which was, I think it was 100 kilograms. 1 kilogram. Okay, that's easy. 1 kilogram, all divided by the radius. And the radius is the radius of the Earth, since we've collapsed. Meters. Okay. Because it's energy, it's going to be equal to joules. 6.67 e to the negative 11th times 1.991 e to the 30th times 1 divided by 6.38 e to the 6th. And so we get negative 2.1 times 10 to the 13th joules, which is a huge amount of energy. At infinity, it's 0. So we've got a decrease in potential energy, which is going to result in a kinetic energy, which is going to cause us huge temperature. Okay, let's just check the answer. So the answer is negative 2.1 times 10 to the 13th joules. Okay, that's it. This is problem 7-38. Okay, it says use the data table 7.3 to find the point between Earth and the Sun at which an object can be placed so that the net gravitational force exerted by Earth and the Sun on the object is 0. Let's just draw a picture of what's going on here. So here's the Sun, here's the Earth. If we put an object right in here, it's going to be pulled towards the Earth, and it's going to be pulled towards the Sun. And I put it closer to the Earth because the Earth has a smaller mass. So to get the same, you want this force from the Sun equal to the force due to the Earth, and therefore they'll be pulling with the same magnitude but in opposite directions. So the force that the Sun's pulling on it is going to be equal to the universal gravitational constant, mass of the Sun times the mass of the object, divided by R in question, or whatever it is. Now one thing is, we're going to figure out this distance. So if this total distance here is r to the sun. The distance from actually has to go all the way to the center. So let's make sure it goes to the center. Okay. So what we're going to know is that let's not do that. So let's say this is r to the object. So we know that this distance, r to the Earth, from this object is that r sub o plus r sub e equals r sub s. And in the case of this calculation is the distance r sub o, and we square that. Whereas the force that the Earth is pulling on it in the opposite direction is still the universal gravitational constant, the mass of the Earth times the mass of the object divided by r sub e squared. And because these are going to be equal to each other, we can set the right-hand sides equal to each other. So we have g times the mass of the sun, the mass of the object, divided by r, 0 squared. And that's equal to g times the mass of the Earth times the mass of the object, divided by r, Earth, which is the distance from the object to the center of the Earth. So we have one of those. We have cancel those out. We cancel the masses out. And we've got two unknowns and one equation, but we also have this second equation. So what we can do is we can just substitute in. We know the distance from the Earth to the sun. That's in the book. So if we say r(O) is r to the sun minus r from the object to the Earth, we make that substitution in here, we'll have one equation and one unknown. So we get the mass of the sun. Instead of this distance, we take the total distance, subtract r sub e. So we have the radius of the sun minus the radius of the Earth. Square that, and that's equal to the mass of the Earth divided by the distance from the Earth to the object squared. Okay, so what do we want to do? We probably want to cross multiply and then expand this out. So we'll get the mass of the sun. There's actually, there's two solutions. There's one where it's on this side and there's one where it's on this side. If it's on this side, it's going to be a little bit further away because the gravitational pull from the sun the distance is a little bit longer, and therefore this also has to be increased. So you'll see that there's two solutions, whether this is going one direction or the other direction. But we're going to do it when it goes where this is on the left-hand side. Okay, mass of the sun times this r sub e, which is what we're solving for. And if we multiply this out, we'll get the radius of the distance from the Earth to the sun squared minus 2r sun r Earth, which is our unknown, plus r sub e squared times the mass of the Earth. Okay, so you can see I have this r sub e thing, and I've got this all. How do I want to do this? We need to get this all on one side and set it equal to 0 and then solve for it. So you're going to have this, and then you're going to subtract that. So we're going to have r sun squared times, well, we're going to multiply times the mass of the Earth. Mass of the Earth, so this times that, and then I'll get 2 mass of the Earth times r sub s, r sub e, -2 times that, and then we'll have the other term, which will be m sub e minus m sub s, m sub e minus m sub s times r sub e squared. It's because I have r sub e squared. And actually I want it, I guess we don't have to change the signs here. So you see we have a quadratic equation. This is the unknown, and this all equals 0. So we could just put it into the quadratic equation where a is the coefficient here, which is m sub e minus m sub s. Is that right? Yes. B is equal to negative 2 m sub e. So that's the coefficient in front of the middle part. And c is the coefficient in front of this, which is going to be, well, it's not the coefficient, because this is just the constant term. So it's going to be m sub e r sub s squared. So then we could just use the quadratic equation. So m r sub e is going to be negative b plus or minus the square root b squared minus 4ac over 2a. So I can go ahead and plug those in, or I could just get numbers and do that. So let's just put the numbers in over here, and then we can plug numbers into the quadratic equation instead of putting all this stuff in here. Okay. So now we go to the back of the book. Look up some, well, we don't have all the numbers in the back of the book, but 5.98 times 10 to the 24th minus the mass of the sun. So we'll get in a second once we figure out what the mass of the sun is. Okay, so that's the B term, and then we have the mass of the Earth, which is 5.98 times 10 to the 24th times the distance to the sun. I just have to get that from 7.3. That's what they asked us to do. Okay, so the mean radius, the distance from the Earth to the sun. 1.496. Up down here. The distance from the Earth to the sun. 1.496 times 10 to the 11th meters. And then we square that. And up here we have the mass of the sun, which is 1.991 times 10 to the 30th power. Okay, so let's get a number. A is going to be, essentially it's going to be this, because that's so small, so let's not even worry, let's ignore that. So we get negative 1.991 times 10 to the 30th. This is only going to make a difference in one of the. Okay, let me take 2 times 5.98. 2 times 5.98. So that's going to be negative 11.96 times 10 to the 24th. That's for B. And C is going to be 5.98 e to the 24th times 1.496 e to the 11th quantity squared. So that's 1.34 times 10 to the 47th power. Okay, so we get negative 11.96 times 10 to the 24th. And we have plus or minus square root of b squared, which is negative 11.96 times 10 to the 24th squared minus 4 times A, negative 1.19 times 10 to the 30th times C, which is 1.34 times 10 to the 47th power, and that whole thing divided by 2 times A, which is negative 11, negative 1.1, negative 1.991 times 10 to the 30th. Okay, let's figure out what's in the parentheses. So we have 11.96 e to the 24th. It's negative, so when it's squared, it's positive. And then we have a negative times a negative. Negative 4 times negative 1.9, so I'm just going to make it positive. Plus 4 times 1.991 e to the 30th times 1.34 e to the 47th power. And then I take the square root of that. Oops, what happened? 1.067 e to the 78th power raised to the 0.5 power. Okay, so this is negative times negative, so we'll get 11.96 times 10 to the 24th plus or minus 1.033 times 10 to the 39th divided by okay. Divided by negative 2 times 1.991 times 2 is 3.982. So we get negative 3.982 times 10 to the 30th. And we're going to take the negative because if we take the positive, then that would create a negative result. So we want the positive result, which is where it's between the two. So we're going to use the negative part here. And you can see this part pretty much drops out because it's so much smaller. So really all we have is 1.033 times 10 to the 39th. Take the negative part of it, divide by negative 3.982 times 10 to the 30th. And so we get 1.033 e to the 39th power divided by 3.982 e to the 30th power. I'm going to get 2.59 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 10 to the 8th meters. So that is the distance of the object from the Earth. And that should be less than the distance to the Sun. Let's go back here. Okay, so the Sun is 1.496 times 10 to the 11th. And our answer is 10 to the 8th, so that's good. And what are they asking us for? This is problem number 38. It's a lot harder than it seems. Not that hard, but it's just a lot of numbers. So find the point between the Earth and the Sun. Okay, so it's this distance from the Earth, and it's going to be another one to it. So let's just check out the answer. Make sure we're doing this thing right. So this is problem number 38. They got 2.59 times 10 to the 8th. 2.59 times 10 to the 8th. Hey, how about that? Okay, so let's go back and review what we just did. I think they must have done it easier than I did. I got the right answer, but so that's interesting. So I set the forces equal to each other. then I use this substitution. I knew the distance to the sun, and then I can relate these two distances. I plug those in for R0. Then I had a quadratic equation, and I just had to solve for it, which was keeping everything straight, which I did. What I'm going to do is I'm going to open up their solution and see what they did differently, and see if they really did do anything differently. So here it is. The equilibrium position lies between the Earth and the Sun on line their centers. At this point, the gravitational forces exerted have equal magnitude in opposite directions. Let this point be distance r from the center of the Earth. That's like my r sub e. Then its distance from the Sun is the distance from the Sun minus r. So here they are. They're set equal to each other. And so what they did then was cancel these things out. And what did how did they get to this point? Oh, they took the square root, so they could get rid of having to do the quadratic equation. Okay, so that's what they did. So they rearranged this, canceled the g out, canceled the m's out, got a ratio of masses, took the square root of both these, and then they didn't have to solve the quadratic equation. Interesting. Okay, this is problem 44. I'm just going to pause it for just a second. Okay, so here we are, 44. And it's Kepler's laws. So we have a satellite which is 600 kilograms, which probably won't come into play because Kepler's laws don't depend upon the satellite. We have the mass of the Earth, which it is orbiting, and so we need that number. I'll try again, I don't know off the top of my head. It's 5.98 times 10 to the 24th kilograms. Okay, about Earth at a height equal to the Earth's mean radius. So the actual radius is going to be the radius of the Earth plus the height, but the height is also the radius, so it's just basically adding it twice. So if you had like that, that's the radius, and then the height would be, so you'd be twice that. So we need the radius of the Earth. That'll be basically 2 times the radius of the Earth will be the radius at which the satellite is orbiting. So the radius of the Earth is 6.38 times 10 to the 6. And the question is, find the satellite's orbital speed, the period of its revolution, and the gravitational force acting on it. So we had that equation, which I don't know if they actually put in the book or not. They have something similar to it, but I'm going to use the one that we have in our notes. And I've forgotten it, so I'm going to derive it. So let's just derive it again. So the equation sets the centripetal acceleration equal to the, or the centripetal force. So it's equal to the gravitational force. So we have m of the Earth, m of the object divided by r squared is equal to the centripetal force, which is going to be equal to mass times the centripetal acceleration, which is that. So the masses cancel out. One of the r's cancel out. So we get v tangential squared is equal to g times the mass of the Earth divided by r. Okay, so that's the equation that we want to use. Now, let's see, think about what they want to do. Orbital speed, well, that's this thing. So we can just solve for the tangential. velocity by taking the square root of both sides. And the radius is 2 times the radius of the Earth. So I'm substituting for r, I'm putting in 2 r sub e. So now we have everything, we just plug the numbers in. So the universal gravitational constant, go to the back of your book, 6.67 times 10 to the minus 11th. Mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by 2, divided by r, which is 6.38 times 10 to the 6th. It should be pretty fast because, you know, things orbit the Earth. You know, it's going to be tens of thousands probably. Thousands or tens of thousands, 11 meters per second. Okay, 6.67 e to the minus 11th times 5.98 e to the 24th divided by 2 divided by 6.38 e to the 6th power. Raise that to 0.5 power, take the square root, and I get 5,590 meters per second. Okay, so that's the speed, and they don't say what units to use, so I think that's going to be fine. Okay, it's period of revolution. Well, think about this. Period T is revolutions per minute, or you could say revolutions per second, something like that. Or it's actually seconds per revolution. Something like that. And so we can do it in seconds, we can do it in, and that's probably good. Or we can do it days. Let's do it seconds. Okay, now, let's think about how this thing works. So we have that omega is equal to, okay, one of the relationships between angular speed and tangential speed is that the tangential velocity is equal to omega times r. And we also know that, what else do we know? We know the frequency is 1 over the period, and we know that frequency is, to remember how this goes, frequency, that's well, that's one way of doing it. Tangential velocity, omega times that. I'm trying to think of the right format to make the most sense. Omega here is in radians per second. Frequency is in basically cycles per second or revolutions per second. So this is in radians per second. So if I calculate, you can see what happens. I can calculate, I've already calculated this, I can calculate omega in radians per second. I can convert that to revolutions per second, because there are 2 pi radians per revolution. And then I could take the inverse to get seconds per revolution. Just looking at it from a unit standpoint. Okay, so let's do that. So omega is equal to the tangential velocity divided by r. 5,590 meters per second divided by the radius, which is the radius of the, not the radius of the Earth, but the radius of the orbit. So it's 2 times the radius of the Earth. And this should be a fairly small number. Omega, so you get 5590 divided by 2 divided by 6.38 e to the 6th power. 4.38 times 10 to the minus 4th radians per second. So let's change that to revolutions per second. So you divide by 2 pi. 4.38 times 10 to the minus 4th radians per second. And we want to get to revolutions per second. So that is, we need radians per revolution, 2 pi radians per 1 revolution. So we divide again, divide by 2, divide by pi, and we get 6.97 times 10 to the minus 4th revolutions per second. So the period, that's omega in revolutions per second, which is the same as frequency. We really don't call it frequency. So let's just get rid of that. But we can take the reciprocal and you'll get seconds per revolution. So we're going to take 1 over 6.97 times 10 to the minus 5th revolutions per second, which will give me seconds per revolution, seconds per rotation. Okay, raise my previous thing to the minus 1 power, and I get 14,300 seconds for the period. And if we divide that by 60, divided by 60, divided by 20, well, we don't need to divide by 24 because we're just going to do how many hours. So 3.98 hours. So if you divide this by 3,600, you get 3.98 hours for it to go about the Earth. So it's going to go around the Earth 6 times in a day. Okay, let me just check the answer. So that is problem number 44. Oh, I haven't finished it. I got one more question to answer. But let me just check here, make sure we're doing it the right way. Okay, so the velocity is 5.59 times 10 to the 9th. So let's go back and see the velocity. 559. Okay, that's right. 3.98 hours. Okay, that's good. And we got one more thing to do, which is the gravitational force acting on it. So all we have to do there is just use universal gravitational expression. So G times mass of the Earth times mass of the object. In this case, we do need the mass divided by R squared. So the force is G, which big G is 6.67 times 10 to the minus 11th. The mass of the Earth is, just reading these out of the back of the book, 10 to the 24th times the mass of the object, which is 600 kilograms, divided by the radius, which is 2 times the radius of the Earth, which is the radius of the Earth is 6.38 times 10 to the 6th meters. So we just plug all those things in, see what we get. So get your calculator out. 6.67 e to the negative 11 times 5.98 e to the 24th times 600, not 300, 600 divided by, and I got to square this, so let me put this squared. 2 times 6.38 e to the 6th, square that, and I get 1,470 newtons. And that should be less than what it is on Earth. On Earth, it would be 600 times 9.8. 600 times 9.8. So the force at the surface is 5880. And I think this should be a fourth because the radius is twice. So if you take 5880 and divide by 4, you get 1470. Okay, so because the radius is twice as much, the gravitational force is 1/4 because we square the radius. So let's just check that. 1,470 newtons. So that's correct. So again, what we did was we said the radius from the center of the Earth to the satellite was twice the radius of the Earth. We derived this, because I forgot what it was, we derived this relationship for objects in orbit. I solved for v sub t, and I plugged the numbers in. G, the mass of the Earth, the radius, and I got 5590 meters per second. Using that, I could calculate the omega, the rotational speed associated with that velocity, and it's just the tangential velocity divided by the radius. And so the rotational speed of the Earth, or that satellite, is this, and converting it to revolutions per second, I divided by 2 pi. I took the reciprocal of that rotational speed, or angular velocity, to get seconds per revolution, which is the period, and I divided by 3600 to convert seconds to hours. So that was the period. And then to find the force, I just used the appropriate values. G, mass of the Earth, mass of the object given in the problem. The radius is twice the radius of the Earth, and you square that, and you find out the force is 1/4 the weight on the surface, because the radius is twice. 2 squared is 4. Okay, this is problem 45. We just finished 44. Similar kind of thing. So we have the mass of the satellite is 200 kilograms. Launched from a site on the Earth's equator into an orbit 200 kilometers above the surface of the Earth. So our radius is going to be the radius of the Earth plus the height. In this case, the height is 200 kilometers, which is 200,000 meters. So convert that to meters. The radius of the Earth, I think it's 6.38 times 10 to the 6th. 6.38 times 10 to the 6 meters. If we write this in scientific notation, it'll get 2.0 times 10 to the 5th meters, or 0.20 times 10 to the 6th meters. So you can see this is not very high above the Earth's surface. The final radius is only going to be 6.58. So R is 6.58. Okay. Assuming a circular orbit, what is the orbital period of the satellite? Well, it's kind of like we just did that. So remember we had tangential velocity squared is equal to G times mass of the Earth divided by R. Is that correct? I've already forgotten it from the previous time. So I don't want to have to derive it again, but I've already forgotten it. So okay, so we have mass V tangential squared over R is equal to G times mass of the Earth times M divided by R squared. Cancel those out. Cancel one of those out. Okay, so that's correct. Okay, now I'm trying to think if there's any easier way of. Well, I think it's because they use this other equation. Why don't we just use the other equation? It's the same kind of deal. T squared is equal to 4 pi squared over G mass of the Earth. There it has sun, but it's the same basic equation. So these are basically the same thing if I put it in terms of period. So if you were for the test, you might want both of these, because this one's good for calculating tangential velocity and this one's good for calculating period. So that's kind of cheating a little bit, but oh well. 4 pi squared. You can see this 2 pi squared. That's where that comes from. Okay. So our radius is this radius, 6.58 times 10 to the 6th meters cubed divided by g, which is 6.67 times 10 to the minus 11th times the mass of the Earth, which is 6.24, 5.98 times 10 to the 24th. So that's the period squared. 4 times pi squared times 6.58 e to the 6th. That whole thing, I got a cube, so I have to insert a parenthesis here. Okay, cubed divided by 6.67 e to the negative 11th divided by 5.98 e to the 24th. So I get 2.82 times 10 to the 1, 2, 3, 4, 5, 6, 7, and that's second squared. So you take the square root of that, and you get 5,310 seconds. And if you divide that by 3,600, you'll get 1.47 hours, which sounds about right. Okay, so that's the period. And then you could use the second equation to calculate the tangential velocity. So that was equal to g actually I'm gonna show you another way. You could use that other equation. We'll do it both ways. So let's just do it here. So you get g, which is I have written down here, 6.67 times 10 to the minus 11th times the mass of the Earth, which is 5.98 times 10 to the 24th divided by the radius, which is 6.58 times 10 to the 6th. That's the velocity squared, 6.67 e to the minus 11th times 5.98 e to the 24th divided by 6.58 e to the 6th, and then take the square root of that. I get, so if you take the square root, you solve for that, you get 7,790 meters per second. Okay, that'll be one way of doing it. Now the other way of doing it is, if you think about the velocity, is delta x over delta t. So the distance it's traveling is going to be 2 pi times the radius that it travels, which is 6.58 times 10 to the 6 meters. So that's the distance it travels in that circle, and the time is going to be equal to 1.47 hours. So 1.47 hours, and then you multiply by 3,600 seconds per hour, and then that'll give you meters per second. 2 times pi times 6.58 e to the 6th divided by 1.47 hours divided by 3,600, and I get 7,810. Just some rounding off. So you see, I got basically the same number, whether I use this formula or whether I use this delta x over delta t. That one's easier for me to remember if I have to use some other way of getting it. Okay, so that was the second part. And the third part is, what is the minimum energy necessary to place a satellite in orbit, assuming no friction? Okay, so how do we do that? Well, what I'm thinking is, if you look at conservation of energy, you have change in kinetic energy plus the change in gravitational potential energy equals 0. And your change in kinetic energy is going to be 1/2 the mass of the object, V final squared minus V initial squared. And the change in potential energy is the calculation from not MGH, but from the definition of potential energy. So remember, potential energy is negative G times, let me see, look that up in the book. Mass of the Earth mass of the object divided by R. Okay, so the change in potential energy, the terms that are constant are the mass of the Earth, the mass of the object, and then you're going to have 1 over R final minus 1 over R initial. This is the only part that changes. R initial is the radius of the Earth, which is given here somewhere. Okay, so the initial radius is the radius of the Earth, which I just looked up. It was 6.38 times 10 to the 6th meters, and the radius final is 6.58 times 10 to the 6th meters. So that's the change in potential energy. So I'm going to just leave this change in potential energy for right now. So the potential energy is increasing. Therefore, the kinetic energy has to decrease. And that equals 0. So we could solve for the initial velocity squared. So let's do that. So if I'm going to solve for this. This goes to the other side, so it's going to be negative the change in potential energy multiplied by 2 divided by the mass. So I'm just multiplying by 2 and dividing by the mass. So you get the final mass for the initial velocity, I think. What is the minimum energy necessary to place the satellite in orbit? Oh, okay, minimum energy. So actually I don't have to, I just have to figure out what the minimum energy is going to be. I guess it's going to be this difference. So it's really just this thing. I'm trying to think if that's, oh, it's actually going to be the minimum energy is going to be this thing right here. It's the initial kinetic energy. So I shouldn't have done that yet. The minimum energy is going to be 1/2 mv initial squared, and so if I solve for that, it's going to be equal to 1/2 mv final squared, and then minus the change in potential energy. What I'm doing is subtracting this from both sides. No, plus. I think that's right. Let's see. Just trying to get my signs right. My negative sign there. Pretty sure. Let me see. Move that to the other side, it becomes negative, but then when I multiply it by -1, it becomes positive. Okay. I'm trying to think. Potential energy is increasing as I go out. It's becoming more positive. Okay, so that's all right. Yes. Okay, so now we're going to plug in all the numbers here. So you get 1/2 the mass. The mass of the object is 200 kilograms times the initial velocity, the final velocity squared, and the velocity was 7,810 meters per second squared, plus the change of potential energy, which is going to be negative G, which is 6.67 times 10 to the minus 11th times the mass of the Earth, which is 5.98 times 10 to the 24th times the mass of the object, which is 200 kilograms. And then there we're going to multiply by 1 over the final radius, which is 6.58 times 10 to the minus, or 10 to the 6th, subtract 1 over 6.38 times 10 to the 6th. And that should give me the answer. Okay, let's do all this. 0.5 times 200 times 7810 squared minus 6.67 e to the minus 11th times 5.98 e to the 24th times 1 divided by 6.58 e to the 6th minus 1 divided by 6.38 e to the 6th. And so I get the answer. And it is 6.1 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 9th joules. So that's the initial kinetic energy that I need to get that thing into orbit. Okay, let's see if that's the right answer. This is problem number 45. Okay, let's check all the answers. Period 1.48 hours. There we go, 1.47, close enough. The rotational speed. 7.79 times 10 to the 3rd. 7.8. Okay, 7 point, close enough. And it says assume the satellite is point initial speed. Oh, it already has the rotational speed. I forgot that part. Yep, it already has an initial kinetic energy. So mine's not quite right. They got 6.43 times 10 to the 9th. And I got 6.5. Where is it? 6.1 times 10 to the 9th. So I think the difference there is that it already had some initial kinetic energy. So I didn't have to provide any more beyond that. I just had to provide something beyond that. So yes, so there was some initial kinetic energy just from it rotating, but you'd have to provide something beyond that. I guess what they're saying is you're putting some work in from the outside, and that has to make up this difference. I see. Okay. Okay, don't worry about that too much. Okay, this is the second example of calculating stuff with satellites. So this is going to be problem number 46 on page 223. So let me read it. A synchronous satellite, which always remains above the same point on a planet's equator, is put in circular orbit around Jupiter to study the planet's famous red spot. Jupiter rotates once every 9.84 hours. Use the date of table 7.3 to find the altitude of the satellite. So it's saying that the period of the planet, which is also going to be the period of the satellite, is 9.84 hours. So let's go ahead and convert that to seconds to start off with. So we have 9.84 times 60, which will give us minutes, times 60, which will give us seconds. So we have 35,400, just round this off, seconds. Okay, so that's the period. Now, as far as the properties of Jupiter, we need to know its radius ultimately to calculate the altitude. But we also know the mass. We need to know the mass. So the mass of Jupiter is 1.90 times 10 to the 27th kilograms. And the radius of it is 6.99 times 10 to the 7th. Okay, so as far as the geosynchronous orbit, well, let's just think about orbiting here in general. And remember, we had two equations. Well, actually, what we were doing was we were relating centripetal acceleration to gravitational force. So if we have centripetal acceleration in terms of omega, which is the rotational speed, so it goes through one revolution in that many seconds, and that equals the acceleration due to gravity that we can calculate, which is going to be equal to g times the mass of the Earth divided by r squared. So it's just the gravitational force without the mass of the object, because force is the weight, mass times gravity, so we take the mass out of there, we'll get that. So what we're trying to do is trying to solve for r. This r is different. That's the r of the planet. So let's just see what we need to do. Solve for r. So what we would get is we would get r cubed is equal to g, the mass. I've got mass of the Earth there. That should be mass, just the mass of the planet. And so let's just call it m. And we divide by r cubed. That's because we divide both sides by r. Sorry. So this is omega squared. So we multiply both sides by r squared, you get r cubed, and you have divide by omega squared. Okay, so you could find it by plugging the information in now, find out what that radius is for given rotational speed, which we don't have yet. So let's do that part next. So we know it takes 2 pi radians for one period. So what we're looking for is radians per second. So the period, we go 2 pi radians in 35,400 seconds. So that'll give us our angular velocity, 2 times pi divided by 35,400. And so I get that the rotational speed of Jupiter is 1.77 times 10 to the minus 4, and it's going to be radians per second. So let's calculate r cubed, and then we'll just take cube root. So we have the universal gravitational constant, which is, I never remember this, so I have to go back, just look in the book and find out someplace where it's actually given in the problem. That's always seems to be the easiest way to do it. Okay, I'm just not going back far enough here. Oh, here it is. Okay, so it's G is 6.673 times 10 to the minus 11th. The mass is in kilograms, and that is right there, 1.90 times 10 to the 27th kilograms. I'm going to just leave those off for right now. As long as everything is in kilograms, meters, and seconds, we're in good shape. Okay, and then we divide by omega squared, which is going to be 1.77 times 10 to the minus 4 radians per second. We're going to square that. And so we would end up with meters cubed as far as the units working out. So let's just plug that in. 6.673 to the negative 11 times 1.9 e to the 20, what did I have written down there? 27th, okay, 27th divided by 1.77 e to the minus 4 exponential, and we square that. And so the radius cubed would be equal to 4.05 times 10 to the 24th. The units are going to be meters cubed, and when we take the cube root of that, so we can do that by taking it to the 1/3 power in our calculator, we'll end up with we'll just round it off to 2 decimal points, 1.6, and we'd have 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th meters. So that's the radius of the, we'll call it radius of S, radius of the satellite. The radius of Jupiter was 6.99, so put R sub j is 6.99 times 10 to the 7th, I think it was, 7th meters. And so our elevation, our height, is just going to be equal to the radius of the satellite minus the radius of Jupiter. And so we have 1.60 times 10 to the 8th minus 6.99 times 10 to the 7th. Put that in our calculator, and I get basically 9.0 times 10 to the 7th meters. So that's my height above the surface of Jupiter. Is that the question they're asking? The question says, find the altitude. So that's the answer. And hopefully that works out. I'll check the answer, and if it's not, I'll let you know. But I'm going to pause the recording. So I've checked the solution manual, and I am correct. The only difference is I might have carried an extra decimal point here, and it could have been 8.9. I think it was, yeah, something like that. So I could have gone probably one more decimal place, but other than that, the solution is correct. So just in review, what we did was we took the period for one revolution, and we could calculate the rotational speed by knowing that we go 2 pi radians in this 2 pi angular radians in this time. And so you take 2 pi divided by the period, and you get the omega, the angular speed. And we solved for, we said that the centripetal acceleration equaled the gravitational force at that particular point, and we solved for r cubed, and we plugged in the numbers g, the mass of Jupiter, divided by the angular speed of the satellite, and there we got a radius of 1.6 times 10 to the 8th. That's the radius of the satellite. To find the actual elevation, we take the difference between these two, and that's where we got the 9.0 times 10 to the 7th. Okay, this is problem 66, and yeah, it's a little interesting. So, hold on just a second. I think my pad needs to be charged up because it's blinking. And don't think it normally doesn't blink, so we'll see what happens here. Okay, so 66, kind of interesting. It's I doubt anybody figured out what to do ahead of time. So you have this person going through various parts of this swing, and so we're going to actually look at 3 particular cases. In all cases, the rope is 4 meters, and then it sweeps through a circular arc. So we have a mass. We have the mass of the person, 70 kilograms. So it asks, when at the beginning of motion, what is the tension in the rope? So here's the person. He's hanging onto the swing. Well, you're going to have the force due to the weight of the person, which is going straight down. The rope is horizontal, so that is not going to cause any tension. And also the tangential velocity is 0 at that point. So the answer for the first part is 0 newtons. There's not going to be any tension in the rope at all. Now the second case is at a height of 1.5 meters above the bottom of the circular arc. So what that means is that this distance is 1.5 meters, which means that the length of this part of this right triangle made this way is 2.5 meters, because 4 minus 1.5 is 2.5 meters. And one thing, so what happens is that from chapter 5, which is conservation of energy, this person is going to have a higher kinetic energy. It's going to have a velocity as it goes through this point. And the velocity is going to be perpendicular to the direction, to the radius. So it's going to be downward like that. And what that's going to cause is to balance this curvature is you're going to have a radius, which is 4 meters, and you're going to have a tangential velocity, which we'll get from energy, and that'll give us a force, which is going to be in this direction. But you also have the weight pulling down the weight of the person, so it has to support both the component of the weight that's going down as well as the centripetal force. Okay, so let's draw a little picture. What does that all mean? So here's the person. And so we have a tension in this rope that's going like that. That's what we're trying to figure out, this tension here. And then you're going to have the weight of the person. And the weight is just the person's mass times acceleration due to gravity. Then you're also going to have a acceleration that's in this direction. Now the question is, yes, okay. So this total tension here is going to be the tension due to the centripetal acceleration, which is going to be exactly in the same direction, plus the component of the weight that is in that direction. So this triangle is also going to be the same as this triangle as far as the dimensions are concerned. And so if we want to put, we could calculate an angle, but we could just really relate these to the ratio of the sides. So I'm going to say this is the hypotenuse, so that's going to be 4, and this is going to be 2.5. Okay, so what does that tell us? We need to figure out what the velocity is at this point. So what you do is use conservation of energy, which says that the change in kinetic energy plus the change in potential energy equals 0. And the change in kinetic energy is equal to 1/2 mv final squared minus v initial squared plus mg times h final minus h initial. Well, V initial is 0, and R particular mass, we can cancel those out. So remember, we've used this before, that V is equal to the square root of 2gh, where h is the difference. So in our case, this will be our velocity, and we get 2 times g times h, which is 2.5 meters, because we are 1.5 meters above the bottom, so that's 2.5 meters. That's our change in height. And so what we would get is 2 times 9.8 times 2.5, raise that to the 0.5 power, which actually turns out to be 7 meters per second. So that's the velocity. Then from that, you calculate the centripetal force, which is going to be the mass times the centripetal acceleration, which is equal to the tangential velocity squared over r. So the centripetal force is the mass, and the mass of the person is 70 kilograms. The tangential velocity is 7 meters per second. We square that, divide by the radius, which is 4 meters, and we'll get 70 times 7 squared, which is 49, divided by 4, and I get 858 newtons. Then you have this component of the force, or the weight, and so what can we say? Well, the weight is 70 kilograms times 9.8 meters per second squared. 70 times 9.8. 70 times 9.8. 686, sorry, newtons. So we can just use the ratio, these triangles, I've got the lengths here. So what we can say is that W sub, we'll call it we'll call it normal for in the direction of the rope, is just going to be equal to the total weight, and we're going to multiply by the ratio of 2.5 to 4. 686 times 2.5 divided by 4. 428 newtons. So the total tension is the sum of these two, 858 newtons plus, which is from the centripetal force and the component of weight in the direction of the rope. So we get 858 plus 428, and that is 1,290 newtons. At the bottom, again, we're going to have a higher velocity. So the velocity at the bottom, again, is the square root of 2gh, but h in this case is 4 meters because we've fallen through the entire distance. So we have 2 times 9.8 times 4, so it should be greater than 7. 2 times 9.8 times 4 raised to the 0.5 power, 8.8, or let's say 8.9 meters per second squared. Now at the bottom we're going to have the weight, and we're also going to have the centripetal force. So this one's actually easier. So the centripetal force is equal to the mass, which is 70 kilograms, times the velocity, which is now 8.9 meters per second. Not squared, just second. Square that. Again, the radius is still 4 meters, so it's going to be greater. 70 times 8.9 squared divided by 4, 1,390 newtons. And then you have the weight, and you take the full amount of the weight, which is 686 newtons. From there, just that, and you add the two together. So the tension at that point is the sum of those two, 1340 1390 plus 686, which is about 2100 newtons. So his weight is this, and so it's almost 3 times his weight is the force that he's got to hold on to that rope with. So now I'm going to check the answer, and this is problem 66. So let me quickly zoom down here. It's going to take a while because it's a pretty, okay, so 66. So it says the tension is 0, and then we have 1.3 kilonewtons. Let's see if that's what I got. So 1.3 kilonewtons is 1,300 newtons. So you can see that rounded off is correct. And the other one is 2,100 kilonewtons, which is exactly what I got. So that is the difference.